Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Hey everyone, welcome back to the Deep Dive.
Glad to be here.
Especially if you're a student pilot aiming for that private pilot license, or maybe just curious about what makes small planes tick. Definitely stick around.
Yeah, this one's for you.
Today we're taking a crucial deep dive into, well, the very heart of your aircraft. The reciprocating engine and the propeller.
These aren't just, chunks of metal. They're complex systems.
Exactly. The systems you'll rely on with every single flight. And really mastering them is key to commanding your plane.
Precisely. Understanding how these components work, their variations, and critically how you manage them, it's fundamental. Not just for the check ride, but for safe, efficient flying for years to come.
Right.
So our mission today, we've got a stack of detailed sources here, mainly from aircraft, reciprocating engines, and propellers. We're going to distill the essential knowledge.
Give you that shortcut to being truly well-informed.
You got it.
Think of it as your insider's guide. What's happening under the cowl, what's spinning out front. So let's unpack this, get you ready to not just fly, but to really understand your aircraft.
Let's start with the engine itself, the powerhouse. Reciprocating engines, the powerhouse beneath the cowl.
Okay, basics first, especially for a student pilot. What is a reciprocating engine, fundamentally? And why is it, the standard in most training aircraft?
Okay, at its core, it's about conversion. Simple as that.
Conversion.
Yeah, converting chemical energy from fuel into mechanical energy. The name reciprocating comes from that back and forth or reciprocating motion of the pistons inside the cylinders. Combustion happens, pushes the piston, turns the crank.
Gotcha.
And why are they so common in trainers? Well, for smaller aircraft, historically, they've offered a great balance of reliability, cost-effectiveness, and a relatively straightforward design. They just work.
So the principle's old, but the engines themselves aren't necessarily stuck in the past. What's new?
Not at all. That's a key point. General aviation has seen some real advances, especially in materials and design lately.
Like what?
We're seeing things like computerized engine management systems. These improve fuel efficiency, cut down emissions, and importantly for you as the pilot, they actually reduce your workload in the cockpit.
Ah, okay. So the core mechanics are similar, but the tech around them is smarter.
Exactly. Now, how they actually ignite that fuel-air mix, that leads to two main designs.
Right, you mentioned ignition methods. What are the big differences a pilot needs to grasp?
Well, the two main camps are spark ignition and compression ignition.
Spark ignition sounds familiar, like a car.
Pretty much. It's been the traditional choice for ages. Use the spark plug, ignites a pre-mixed fuel-air mixture. Simple, effective.
And the other one, compression ignition.
Right. These are often called jet fuel piston engines, and they're definitely gaining ground.
Jet fuel in a piston engine.
Yep. Instead of a spark plug, they compress the air in the cylinder so much that it gets incredibly hot. Then they inject the fuel, and it ignites automatically from the heat and pressure.
Huh. So what's the advantage there for a pilot?
Several things, actually. Often lower operating costs because jet fuel can be cheaper or more available than avgas in some places. They tend to be very reliable, simpler in some ways, no spark plugs or magnetos needed.
Okay, so same basic moving parts, pistons, cylinders, but totally different ways to kick off combustion. Fascinating physics.
It really is.
Beyond ignition type, how else are these engines classified? What should a student pilot know?
Good question. We also categorize them by how the cylinders are arranged around the crankshaft. You've got radial engines, think old warbirds, inline engines, V-type engines, or opposed engines. Then there's the operating cycle, two-stroke or four-stroke, and how they're cooled liquid or air.
Okay, that's a lot of types. For the typical trainer, say a Cessna 172 or a Piper Archer, what are we most likely looking at?
Almost certainly you'll be flying behind a horizontally opposed engine.
Horizontally opposed. Why that one?
Well, this design always has an even number of cylinders lying flat and opposing each other across the crankcase.
Okay.
They give you a really good power-to-weight ratio. They're compact, which means less funnel area, less drag, better streamlining. And most of them are air-cooled, which simplifies things.
Makes sense. Efficient, reliable package for training.
Exactly.
So, let's dig into the most common type found in GA, the four-stroke. What's actually happening inside those cylinders, stroke by stroke?
Right, the four-stroke spark ignition cycle. Think of it as the engine's heartbeat. 4 distinct piston movements for every single power pulse. Understanding this isn't just, academic knowledge for the written test.
No.
No, it's key to recognizing when something sounds or feels off. When one cylinder isn't pulling its weight, that's often your first clue something's wrong.
Okay, break it down. The 4 strokes.
First, intake. Piston moves down, the intake valve opens, and it sucks that fuel-air mixture into the cylinder. Second, compression. Intake valve closes, piston moves up, squeezing that mixture tight. More compression generally means more power potential.
Got it.
Third, power. Bang. Spark plug fires, the mixture ignites, huge pressure slams the piston down. This is what actually turns the crankshaft and ultimately the propeller.
The money stroke.
That's the one. And finally, fourth, exhaust. Exhaust valve opens, piston moves back up, pushing out the burnt gases. Then the whole cycle repeats.
Intake, compression, power, exhaust. And that's happening incredibly fast in multiple cylinders, all timed perfectly.
Hundreds, even thousands of times per minute. It's a precise mechanical dance, relying on all those auxiliary systems: induction, ignition, fuel, oil, cooling, exhaust, working together.
And you mentioned earlier, it's not just about traditional avgas engines anymore. This diesel or jet fuel thing is real.
Absolutely. The integration of diesel technology or compression ignition is a significant development, pioneered way back, but really taking off now.
So are these engines actually flying, or still mostly experimental?
Oh, they're flying. Definitely in service. Engines from companies like Thielert, now Continental, and SMA.
On what kind of planes?
You'll find them on modern aircraft like the Diamond DA-40 and DA-42, and they can even be retrofitted onto classics like the Cessna 172 and the Piper PA-28 family.
Wow. And the big deal for pilots besides fuel type?
Often it's the engine management. These modern diesel engines are frequently paired with FADC full authority digital engine control.
FADC. We'll circle back to that. Sounds important.
It is. It dramatically simplifies how you manage the engine. Big workload reduction.
Turning power into thrust.
Okay, so we've got this engine making power, but how do we actually use that power to, fly? That's the propeller's job, right? Turning rotation into thrust.
Exactly. The propeller is what translates the engine's rotational power into the force that pulls or pushes the aircraft through the air.
How does it actually do that? Is it like a fan?
Think of it more like a rotating wing, seriously. Each propeller blade is an airfoil, just like your aircraft's wing. So it's subject to the same aerodynamic principles: angle of attack, lift, which we call thrust in this case, induced drag. It can even stall. The engine spins it, and its shape and angle create a pressure difference that generates thrust.
And the amount of thrust depends on?
Depends on the blade's shape, its angle of attack, how it meets the air, and how fast the engine is spinning it, the RPM.
And I remember reading the blade isn't just flat, it has a twist to it. Why is that?
That twist is absolutely critical. It's maybe one of the most important design features of a propeller.
Why so critical?
Because the tip of the propeller blade travels much faster than the part near the hub, right? It covers more distance in the same amount of time.
Right, bigger circle.
Exactly. So if the blade had the same angle all the way along, the tip would be at a really high angle of attack, probably stalled, while the root might even have a negative angle. Super inefficient. The twist compensates for this difference in speed. The blade angle is highest, greatest pitch, near the hub, and lowest, smallest pitch, near the tip. This ensures that the angle of attack is relatively consistent along the entire blade length, producing uniform thrust. It's quite clever.
Yeah, that makes sense. Keeps the whole blade working together. So, for us student pilots, what are the main types of props we'll likely encounter on typical training aircraft?
You'll primarily deal with 2 main categories: fixed pitch propellers and adjustable pitch propellers.
Okay, let's start with fixed pitch. Sounds simple.
It is. The name says it all. The angle of the blades, the pitch, is fixed. Set by the manufacturer, can't be changed by the pilot in flight.
Advantages.
Simplicity, low weight, lower cost, pretty robust.
Disadvantages.
Efficiency. A fixed pitch prop is really only truly optimal at one specific combination of airspeed and RPM.
So it's a compromise.
Exactly. You have to choose what you want to optimize for. You can have a climb prop or a cruise prop.
That's the difference.
A climb prop has a lower pitch, like a lower gear in a car. Less drag, allows the engine to reach higher RPM easier, better for takeoff and climb performance.
But not great for cruising fast.
Right. It'll limit your top speed and cruise efficiency. A cruise prop has a higher pitch, like a higher gear. More drag at low speeds, lower RPM for a given power setting, but it's more efficient once you get up to cruise speed.
So you trade off takeoff performance for cruise speed.
You got it. And with a fixed pitch prop, your main way of monitoring engine power output is the tachometer it shows you, engine RPM.
Just RPM.
Primarily, yes.
Yeah.
But remember, and this is important, RPM alone isn't a perfect measure of power, especially as you change altitude.
How so?
Because the air gets less dense as you go higher. So 2,300 RPM at 5,000 feet is actually producing less horsepower than 2,300 RPM down at sea level. You'll find you need to open the throttle more at higher altitudes just to maintain the same RPM.
Okay, good point. Tachometer is key, but density altitude matters. Now, what about adjustable pitch props? Are these the constant speed ones?
Generally, yes. Technically, there were ground adjustable props where you could change the pitch on the ground, engine off. But practically speaking, when we say adjustable pitch today in GA, we mean constant speed propellers.
Constant speed? How do they work?
These are controllable pitch props where the blade angle is automatically varied in flight by a device called a propeller governor.
Automatically. What's the big advantage for a pilot then?
Efficiency. Big time. A constant speed prop lets you, the pilot, select the most efficient engine RPM for a given phase of flight, say climb or cruise, and the governor automatically adjusts the propeller blade angle, pitch, to maintain that selected OPM, regardless of changes in airspeed or engine power output.
So it optimizes the prop pitch for the situation.
Precisely. It converts a much higher percentage of the engine's brake horsepower into useful thrust horsepower across a wider range of conditions compared to a fixed pitch prop.
Okay, so that means more controls in the cockpit for me to manage, right?
Correct. With a constant speed prop, you typically have two main engine controls. The throttle, like before, which controls engine power output, and a separate propeller control lever, often blue, which sets the desired RPM you want the governor to maintain.
So I set the RPM I want with the prop lever,
Okay.
and the governor does the work of changing blade pitch.
Exactly. You set, say, 2,400 RPM for climb, and the governor adjusts the blade pitch to hold 2,400 RPM as you accelerate or pitch up or down. If the engine tries to speed up, the governor increases the blade pitch, takes a bigger bite of air to slow it down. If it tries to slow down, the governor decreases pitch to let it speed back up to the set RPM.
Clever. But if RPM isn't the main power indicator anymore, how do I know how much power I'm actually making?
Great question. With a constant speed prop, your primary power indicator is the manifold pressure gauge, or MAP gauge.
Manifold pressure, what's that measuring?
It measures the absolute pressure of the fuel-air mixture inside the intake manifold, after the throttle valve, but before it enters the cylinders. Think of it as how much boost or pressure is pushing that mixture into the engine.
So higher MAP means more fuel-air mix means more power.
Generally, yes. You open the throttle, MAP increases, indicating more power output.
Yeah.
Close the throttle, MAP decreases.
What does it read when the engine's off?
It'll show the current ambient atmospheric pressure. When the engine's idling, it'll show a very low pressure because the throttle is mostly closed, creating a vacuum.
And if it suddenly goes up to ambient pressure in flight?
It could be a sign of engine failure or power loss. The engine is no longer drawing air in strongly. Like the RPM gauge, it'll have green arcs for normal operation and a red line for the maximum allowable manifold pressure.
Okay, throttle for MAP, prop lever for RPM.
Yeah.
Now, here's something I know is super important, especially for the check ride and just not breaking the engine. The order you adjust these controls.
Absolutely critical. Getting this wrong can seriously overstress the engine.
So lay it out for us. Decreasing power.
When decreasing power, always reduce the manifold pressure, first using the throttle, then reduce the RPM using the prop control.
Why that order?
If you reduce the RPM first, pull the prop lever back, the governor will try to maintain that lower RPM by increasing the blade pitch. This increases the load on the engine, which can cause the manifold pressure to spike, potentially exceeding the red line. Not good.
Okay, MAP first, then RPM when reducing power. What about increasing power?
Reverse the order. Increase the RPM first with the prop control, then increase the manifold pressure with the throttle.
Got it. RPM up, then MAP up. Prevents overboosting on the way up too.
Exactly. And always check your specific aircraft's POH or AFM for the manufacturer's recommendations. There might be specific limits or procedures, especially regarding high RPM, low MAP operations in some engines.
Right. POH is king. Now, speaking of propellers and potential issues, there was an interesting FAA safety bulletin about propeller overspeed. This seems really relevant for student pilots understanding potential failures.
Yes, the SAIB, Special Airworthiness Information Bulletin. It highlighted a real-world incident. Single-engine plane, cruise flight, and suddenly the propeller overspeeds RPM goes way too high, and the pilot experiences almost no thrust.
What caused it?
It was a failure inside the propeller hub, in the mechanism that changes the blade pitch. It failed in a way that forced the blades to their low pitch stop, basically, a maximum RPM, minimum thrust position. It's like being stuck in first gear at highway speed.
Okay, so the prop was spinning really fast but not grabbing much air. What did the pilot do?
The pilot, following standard procedure, attempted to glide at the published best glide speed, VG, towards an airport, but didn't make it and had to land off-field.
So what was the key takeaway, the aha moment from the FAA's analysis?
The analysis showed something counterintuitive. For that specific failure mode, gliding at a lower airspeed than VG would have actually allowed the propeller, even stuck in low pitch, to generate more thrust, potentially enough to maintain level flight or at least extend the glide significantly.
Wow. So the standard best glide speed isn't always the absolute best answer in every single engine out or partial power scenario.
In this specific type of propeller overspeed failure, potentially not. It raises a crucial point for pilots. While your POH procedures are your primary guidance, especially in an emergency,
Right.
you need to be aware that in certain rare failures, like this prop overspeed where you still have some engine power but minimal thrust at normal speeds, experimenting with a reduction in airspeed, if you have the altitude and time to safely assess, might yield a better outcome.
That's a really important nuance. Fly the plane, follow the procedure, but be aware that sometimes physics might offer a slightly different solution if you have the capacity to analyze.
Precisely. It's about understanding the systems deeply enough to potentially adapt safely when the standard answer isn't working as expected. Again, only if altitude and time permit careful assessment. 3. Engine systems. The supporting cast for flight.
Okay, we've covered the engine basics and the prop. But there's a whole bunch of other systems working behind the scenes to make it all happen right. Let's start with how the engine breathes, the induction system.
Right. The induction system's job is simple. Get outside air, mix it with the right amount of fuel, and deliver that combustible mixture to the cylinders.
Where does it start?
Usually an air intake port on the front of the cowling, often covered by an air filter to keep out dust, bugs, debris.
What happens if that filter gets totally clogged, say by ice or something?
That's where a critical safety feature comes in, an alternate air source.
Alternate air.
Yeah. Usually it pulls air from inside the engine cowling itself, bypassing the clogged filter. It might be automatic, or you might have a manual control for it. The key is ensuring the engine doesn't suffocate.
Makes sense. So two main ways this fuel-air mixing happens in the small aircraft we fly.
Primarily, yes. You've got carburetor systems and fuel injection systems.
Carburetors. That sounds like older technology, maybe.
Yeah.
How does a typical float-type carburetor work?
It's a classic design. Filtered air flows into the carburetor body and gets squeezed through a narrow pinched section called a venturi.
Venturi, like an hourglass shape.
Kind of, yeah. Physics tells us that when air speeds up to that narrow throat, its pressure drops significantly.
Okay.
This low pressure zone is used to suck fuel from a small reservoir inside the carburetor,
Yeah.
maintained at a constant level by a float through a little tube called the main jet. The fuel atomizes and mixes with the fast-moving air.
And then that mixture goes off to the cylinders.
That's the gist of it. Simple, but it has some drawbacks.
Like what? What are the downsides for pilots?
Well, float-type carburetors don't always handle abrupt maneuvers while the fuel can slosh around. Fuel vaporization isn't always perfect. But the biggest one, the one every student pilot must understand, is their susceptibility to carburetor icing.
Carb ice? Okay, this comes up constantly in training. Why is it such a big deal? Can it really happen even if it's not freezing outside?
Absolutely. Yeah. And that's why it's so insidious. Carb ice doesn't care much about the outside air temperature. It forms because of the physics inside the carburetor venturi.
How?
Two things happen simultaneously in the venturi. The air pressure drops dramatically, which causes cooling, and the fuel vaporizes, turns from liquid to gas, which also requires heat and causes significant cooling.
So it gets really cold right inside the carb throat.
Extremely cold. That temperature drop can be 60, even 70 degrees Fahrenheit, or about 33, 38 Celsius below the outside air temp.
Wow. So you could have ice forming inside the carburetor when it's like 80 degrees F outside?
Easily.
Yeah.
Especially if there's moisture in the air.
Yeah.
The FAA says it can happen at temps up to 100 degrees F, 38 degrees C, with humidity as low as 50%. The ice builds up on the surfaces inside, including the throttle valve, restricting the flow of the fuel-air mixture.
What does that do to the engine?
It reduces power, makes the engine run rough, and if it gets bad enough, it can completely block airflow and stop the engine. Dead stick.
Scary. And you said it's worse at reduced power settings.
Yes, like during descents. With the throttle partially closed, the throttle valve itself can get iced over, and because the engine isn't demanding as much air, the ice can build up faster, and you might not notice the gradual power loss until it's significant.
Okay, how do we spot carb ice forming? What are the symptoms?
Depends on your propeller type. If you have a fixed-pitch prop, the first sign is usually a decrease in engine RPM. You might also notice the engine starting to run rough.
And with a constant speed prop?
With a constant speed prop, you won't see an RPM drop initially because the governor will automatically decrease the blade pitch to try and maintain the set RPM. Instead, you'll see a decrease in your manifold pressure, MAP. Engine roughness might follow.
So RPM drop for fixed pitch, MAP drop for constant speed. Got it. How do we fight it?
Aircraft with float-type carburetors are equipped with a carburetor heat system.
Carb heat, what does it actually do?
It routes hot, unfiltered air from a shroud around the exhaust muffler into the carburetor intake before the venturi. This preheats the air enough to prevent ice from forming or melt ice that is already formed.
Unfiltered air.
Yes, which is why you typically don't use carb heat on the ground where it could suck in dust or dirt. But in the air, it's your primary defense and cure for carb ice. It also serves as that alternate air source if the main air filter gets blocked.
Okay, so if I suspect carb ice, RPM dropping, MAP dropping, engine running rough, what's the procedure?
Apply full carburetor heat immediately. Don't be timid, put it all the way on.
Full heat? Why not just a little bit?
Because partial heat might not be enough to melt the ice and could even make things worse by melting some ice which then refreezes elsewhere, or by creating a slushy mix that's just as bad. Full heat ensures the temperature gets well above freezing.
And leave it on.
Leave it on until you are absolutely certain all the ice is gone. You should expect a further drop in engine power when you first apply carb heat.
Why a drop? Isn't it supposed to help?
Because the hot air is less dense than cold air. Less dense air means less oxygen per volume, so the engine produces slightly less power, maybe up to a 15% decrease. You'll also likely see the engine run even rougher for a short period as the melting ice gets ingested.
Okay, so expect a drop in power and maybe more roughness initially. Then what should happen?
If ice was present after the initial drop in roughness, you should see a gradual increase in RPM, fixed pitch, or MAP, constant speed, as the ice melts and the engine breathes freely again. The engine should also smooth out.
And if no ice was present?
If there was no ice, you'll just see the initial power decrease from the hot, less dense air, and it will stay there until you turn the carb heat off.
When should I not use carb heat?
You generally avoid it when you need full power, like during takeoff, unless icing conditions are severe and the POH directs otherwise. And avoid continuous use during normal cruise unless conditions are conducive to icing or you're checking for it. Some planes have a carb air temp gauge with a yellow arc. You'd use heat to keep the needle out of that potential icing range.
Okay, carb ice, sneaky, dangerous, but manageable with prompt, full carb heat application. Now, what about fuel injection? You said it's less prone to this.
Correct. Fuel injection systems don't have that venturi where the major temperature drop occurs because they inject fuel directly into the cylinders or just upstream of the intake valve.
How do they work broadly?
They typically use an engine-driven fuel pump to deliver fuel under pressure to a fuel air control unit. This unit meters the fuel flow based on throttle position and air density, sending it through lines to discharge nozzles at each cylinder. There's usually an electric auxiliary fuel pump too for starting and as a backup.
So what are the advantages for pilots besides less carb ice risk?
Several. Better fuel flow, each cylinder gets a more precise amount. Faster throttle response, more precise control over the fuel-air mixture, which helps with leaning for efficiency. And often they're easier to start in cold weather.
Any downsides? Carburetors sound simpler in some ways.
They do have a couple of quirks. Fuel-injected engines can sometimes be harder to start when they're hot, a condition called vapor lock, where fuel vaporizes in the lines. Restarting after running a tank dry can sometimes be trickier too.
And are they totally immune to icing?
They're immune to carburetor icing, the evaporative kind, but they are still vulnerable to impact icing, where ice builds up on the air filter or inside the air intake duct itself, blocking airflow. That alternate air source is still important.
Good distinction. Evaporative icing versus impact icing. Okay, moving on. For pilots wanting to fly higher performance aircraft or just get more power at altitude, we have things like superchargers and turbochargers.
Right, forced induction systems. Both do the same basic job. They compress the intake air before it goes into the engine.
Why compress it?
To increase its density. Denser air contains more oxygen molecules per volume. More oxygen allows you to burn more fuel, and burning more fuel makes more power. It counteracts the natural power loss that occurs as you climb into thinner air.
Okay, makes sense. What's the difference between a supercharger and a turbocharger?
The key difference is what drives the compressor. A supercharger is mechanically driven by the engine itself, usually through gears or a belt. It takes some engine power to run it.
So it forces more air in, boosts manifold pressure, even at altitude.
Exactly. It allows an engine to maintain sea level power, or even produce boosted power, up to a certain altitude. Some big radial engines back in the day even had two-speed superchargers for different altitude regimes.
And a turbocharger or turbo supercharger.
A turbocharger is generally considered more efficient because it uses energy that would otherwise be wasted. The engine's hot exhaust gases.
How does that work?
The exhaust gases spin a turbine wheel, which is connected by a shaft to a compressor wheel on the intake side. So the exhaust energy spins the turbine spins the compressor, and the compressor forces denser air into the engine. It's essentially recycling waste heat energy.
Clever. Free power, almost.
Well, not quite free. There's weight and complexity, but it doesn't directly rob engine crankshaft power like a supercharger does.
Yeah.
A big advantage of turbocharging is allowing an engine to maintain its rated sea level horsepower all the way up to its critical altitude.
Critical altitude.
That's the maximum altitude at which a turbocharged engine can still produce its full rated sea level power. Above that, power will start to decrease, but much less dramatically than a normally aspirated engine.
How does the pilot control the amount of boost from a turbo?
Turbo systems have a crucial component called a wastegate. It's basically a valve in the exhaust system before the turbine.
What does it do?
It controls how much exhaust gas actually flows through the turbine. When the wastegate is partially open, some exhaust bypasses the turbine, so the turbo spins slower and produces less boost. When it's closed, all the exhaust goes through the turbine, spinning it faster and making more boost.
Are these manually controlled?
Some older systems were, requiring very careful monitoring of the MAP gauge to avoid an overboost exceeding the engine's manifold pressure limits, which can cause serious damage. Most modern systems are automatic or semi-automatic, using pressure sensors to control the wastegate and maintain the target manifold pressure set by the pilot's throttle.
Any special considerations for pilots flying turbocharged planes? Things to watch out for?
Definitely. Turbos spin incredibly fast. Think over 80,000 RPM and get extremely hot from the exhaust gases.
Yeah.
So engine oil is critical, not just for lubricating the engine, but for lubricating and cooling the turbocharger's bearings. You need to make sure your oil temperature is within the normal operating range before applying high-power settings.
And after landing.
Equally important. Don't just chop the power and shut down immediately after running at high power. You need to let the engine idle for a few minutes to allow the turbocharger to cool down and slow down gradually.
Why is that?
If you shut down a very hot turbo abruptly, the oil flow stops. But the turbo is still incredibly hot. The residual oil inside can literally cook, forming carbon deposits called coke. These deposits can block oil passages and eventually lead to turbo failure. So, proper cool down is essential for longevity.
Okay, good tips. Oil temp before high power, cool down before shutdown. Let's talk ignition for those spark ignition engines. We need a spark to get things going.
Right. The ignition system delivers that high-voltage spark to the spark plugs at precisely the right moment. Key components are the magnetos, spark plugs, high-tension leads, wires, and the ignition switch in the cockpit.
Magnetos. What's special about them? Why not just use the aircraft battery?
This is a crucial safety feature. Magnetos are engine-driven electrical generators that produce their own high-voltage electricity completely independently of the aircraft's main electrical system and battery.
So even if the entire electrical system fails, the battery dies, the alternator quits.
The magnetos keep firing the spark plugs as long as the engine crankshaft is turning. They use permanent magnets and rotating coils to generate the current needed. Huge redundancy factor.
And most planes have two of them. Why two?
Redundancy again, plus performance. Almost all certified aircraft engines have a dual ignition system. Two separate magnetos, each firing its own set of spark plugs, usually one plug per magneto in each cylinder, so 2 plugs per cylinder.
So if one magneto fails?
The other one keeps the engine running, likely with only a very slight drop in power. Having 2 spark plugs firing in each cylinder also promotes smoother, more complete combustion of the fuel-air mixture, which actually gives a little bit more power than a single plug would.
Okay, makes sense. The ignition switch in the cockpit usually has positions like OFF, R, L, both start.
Correct. Off grounds both magnetos, preventing them from firing. R selects only the right magneto, L selects only the left magneto, both selects both for normal operation, and start engages the starter motor while usually firing one or both magnetos, depending on the system.
And that magneto check we do before takeoff is really important for student pilots to understand. What are we actually checking?
It's a critical check. During the run-up at the recommended RPM, you switch the ignition from both to R, then back to both, then to L, then back to both.
What should happen?
You're looking for a small, allowable drop in RPM when running on only one magneto compared to running on both. Check your POH for the specific allowable drop, typically around 50-75 RPM, and the maximum difference allowed between the L and R drops.
What does that drop tell us?
It tells you that both magnetos were working when you were on both,
Yeah.
because disabling one causes a slight power loss, hence RPM drop. It also confirms that each magneto can run the engine independently.
What if the engine completely quits when I switch to R or L?
That's a no-go item. It means that magneto has failed. Do not fly until it's fixed.
What if the RPM drop is bigger than the limit in the POH?
Also a no-go. It could indicate fouled spark plugs, incorrect timing, or other issues with that ignition system. Needs investigation.
What about if there's no RPM drop at all when switching from both to R or L? Is that good?
No, that's actually not normal and also requires checking before flight. It usually means the magneto switch isn't properly grounding the magneto it's supposed to be shutting off. This could lead to issues later or hide a problem with the other magneto.
Okay, crucial checks. And speaking of magnetos and safety, that scary warning about moving the prop.
Yes, this cannot be stressed enough. Because magnetos generate their own power whenever the engine turns, even if the main battery and master switches are completely O-off-F.
Uh-oh.
If the ignition switch is accidentally left in the both L or R position, instead of O-F-F, and someone moves the propeller, the engine can fire and start unexpectedly.
Seriously, even with everything else off.
Seriously. It's called a hot mag. It's a major cause of injuries and fatalities on the ramp. Always, always treat the propeller as if it could start at any moment. Confirm ignition O-off-F, yell clear prop before moving it to starting. There's also a rarer scenario where if the grounding wire, P-lead, between the magneto and the switch is breaking, the magneto could be hot even when the switch is turned off-F.
So if the engine starts even with the switch off?
The only way to stop it is usually by pulling the mixture control to idle cutoff, starving it of fuel. Prop safety is paramount.
Absolutely. Okay, let's talk oil, the engine's lifeblood. What does it actually do besides lubricate?
Oil is a real multitasker in the engine. Yes, lubrication of moving parts is primarily reducing friction and wear, but it also plays a huge role in cooling.
Cooling?
Yep. It absorbs heat directly from hot engine parts, like the pistons and cylinder walls, and carries that heat away, usually to an oil cooler radiator. It also provides a seal between the piston rings and the cylinder walls to prevent combustion gases from blowing by. And finally, it helps clean the engine by carrying away contaminants and debris to the oil filter.
Wet sump versus dry sump. What's usually in our trainers?
Small aircraft engines almost always use a wet sump system. This means the oil supply is stored in a sump, which is basically an oil pan attached to or integral with the bottom of the engine. An oil pump draws oil from the sump, circulates it through the engine and filter, and cooler if equipped, and then it just drains back down into the sump.
Simple enough. Dry sump is for bigger engines.
Yeah, dry sump systems have a separate external oil tank and are typically found on higher performance aerobatic aircraft or very large engines where a wet sump isn't practical.
What gauges do we monitor for oil in the cockpit?
Two main ones, the oil pressure gauge and the oil temperature gauge.
What's normal for pressure?
The pressure gauge gives you a direct reading, usually in PSI. It should come up into the green operating arc very quickly after engine start. Low or zero oil pressure is an emergency land as soon as possible. High pressure can also be a problem. Red lines indicate minimum and maximum limit.
Temperature.
Oil temperature changes much more slowly. It tells you if the oil is getting too hot, which could indicate a problem like low oil level, a blockage, or engine overheating. Or if it's too cold, which might happen in very cold weather before takeoff. Again, there's usually a green arc for the normal operating range.
And checking the oil itself before flight.
Absolutely essential part of your pre-flight. You'll check the oil quantity using the dipstick, making sure it's between the minimum and maximum marks specified in the POH. Also, make sure you use the correct type and weight viscosity of oil recommended by the engine manufacturer for the current climate conditions. Using the wrong oil can cause serious damage.
Got it. Check level, check type. Okay, engines make a ton of heat from combustion. How do we get rid of it all so things don't melt?
Right, managing heat is critical. Oil helps with internal cooling, as we said, but you need a way to cool the outside too, especially the cylinders and cylinder heads where combustion happens.
How do most small planes do it? Liquid cooling like a car.
Most are actually air-cooled. It's simpler and lighter than liquid cooling.
How does air cooling work?
The engine cowling is designed to scoop in ram air through front openings. Inside the cowling, there are metal shields called baffles that direct this airflow tightly over cooling fins cast onto the cylinders and cylinder heads.
Fins, like on a motorcycle engine?
Exactly like that. Those fins dramatically increase the surface area exposed to the airflow, allowing heat to transfer efficiently from the metal to the air. The heated air then exits through openings, usually at the bottom or rear of the cowling.
When is air cooling less effective?
It relies heavily on forward airspeed to force air through the cowling, so it's least effective during ground operations, especially idling for long periods, takeoffs, and slow, high-power climbs or go-arounds. That's when engine temps can get high.
And the opposite, too much cooling.
Yes, that can happen too, especially during long descents at low power settings and high airspeed. This can lead to shock cooling, where the engine temperature drops too rapidly, potentially causing stress or damage, like cracked cylinders. Gradual power reductions and avoiding prolonged high-speed descents at idle can help prevent this.
What gauges help us monitor engine temperature directly?
Besides the oil temp gauge, which is indirect, many aircraft have a cylinder head temperature gauge, or CHT. This gives you a direct temperature reading from one or more cylinder heads. It reacts much faster than oil temp and is a primary indicator of potential overheating. It'll have a green arc and a red line maximum.
So if my CHT is climbing too high, what can I do as a pilot?
Several things. You can increase airspeed, like lowering the nose slightly in a climb, to force more cooling air through the cowling. You can enrich the fuel-air mixture. A richer mixture burns cooler. And you can reduce power.
What about those cowl flaps some planes have?
Right. Some higher performance aircraft have cowl flaps. These are adjustable doors or shutters on the cowling exit area.
What do they do?
You can open them, usually for takeoff, climb, and ground ops, to allow maximum airflow and cooling. You can close them partially or fully, usually in cruise flight, to reduce cooling drag and help the engine maintain its optimal operating temperature. They give you direct control over cooling. If temps get too high, open the cowl flaps. If the engine is running too cool, close them.
Okay, another system to manage. Now, the exhaust system seems simple, just get rid of the Bren gases. Does do anything else?
It often does more than just vent exhaust overboard safely away from the cabin and intakes. In many small aircraft, the hot exhaust muffler is used to provide cabin heat and sometimes windscreen defrost.
How does that work? Is it safe?
There's usually a metal shroud or enclosure around the muffler. Clean outside air is ducted into this shroud, gets heated by contact with the hot muffler surface, and then this heated air is piped into the cabin when you turn the heater on.
What's the big safety concern there?
Carbon monoxide, CO. Engine exhaust contains extremely high concentrations of this odorless, colorless, tasteless, but deadly gas.
So if the muffler has a crack or leak?
That CO could leak directly into the cabin heating shroud and get pumped right into the cockpit. This is why regular exhaust system inspections are critical, and why having a working CO detector in the cockpit is highly recommended, if not required.
Absolutely crucial point. CO is no joke. Does the exhaust system do anything else performance-wise?
Some systems incorporate an exhaust gas temperature, EGT probe. This measures the temperature of the exhaust gases as they leave the cylinder.
What's that used for?
EGT is very sensitive to the fuel-air mixture ratio. Pilots use the EGT gauge as a precise tool for leaning the mixture in cruise flight. By carefully adjusting the mixture control and watching the EGT, you can find the setting that provides the best fuel economy or best power for your altitude and power setting according to the POH.
Ah, okay. EGT for precise leaning. Got it. How about starting the engine? What's involved there?
Most trainers use a direct cranking electric starter system. You've got the aircraft battery, wires, a solenoid, and the starter motor itself.
What happens when I turn the key or switch to start?
Power from the battery flows through the solenoid to the starter motor. The starter motor engages a gear onto the engine's flywheel or ring gear, spinning the engine crankshaft over. As the engine spins, the magnetos fire, fuel mixture gets drawn in, and hopefully combustion starts and the engine fires up and runs on its own.
Any key safety reminders for starting, besides the prop danger we already covered?
Always make sure the aircraft is properly secured, brakes set, chocks in place if possible. Ensure the area around the prop is clear of people, equipment, and especially loose gravel or debris that the prop blast could kick up and damage the plane or hurt someone. Follow the specific starting checklist in your POH carefully.
Right, checklists and vigilance. Okay, last couple of engine topics, and these sound nasty. Detonation and preignition. What are these, and why should pilots be worried?
These are two abnormal combustion events that can cause serious engine damage very quickly. They are definitely things you want to avoid.
Let's start with detonation. What is it?
Normal combustion is a smooth, controlled burn of the fuel air mixture, initiated by the spark plug. Detonation is like an explosion, an uncontrolled, instantaneous, violent ignition of the remaining unburned fuel air mixture in the cylinder after the spark plug is already fired.
Like a secondary explosion, what causes that?
It happens when the temperature and pressure inside the cylinder get too high for the fuel's octane rating. The fuel literally auto-ignites under the pressure. Common causes include using a lower fuel grade, lower octane, than specified for the engine.
Using the wrong gas.
Exactly. Also, operating with excessively high manifold pressure combined with low RPM, especially in turbocharged or supercharged engines. Running the engine too lean at high power settings can also cause it. And prolonged ground operations or steep climbs where engine cooling is reduced can raise cylinder head temperatures enough to induce detonation.
What are the symptoms? How would I know it's happening?
Severe detonation can sound like hammering inside the engine and cause immediate failure. Less severe cases might cause engine roughness, loss of power, and most noticeably, excessively high cylinder head temperatures, CHT. If you see your CHT climbing rapidly towards or past the red line, detonation could be occurring.
What can it damage?
It puts tremendous stress on pistons, cylinder heads, valves. It can break piston rings, crack pistons, damage valves, potentially leading to complete engine failure if not corrected quickly.
So how do pilots avoid detonation?
Number 1, always use the correct fuel grades specified in the POH. Number 2, operate the engine within its limitations. Avoid excessive mag-plow RPM combos. Don't overlean at high power. 3, ensure adequate cooling. Use cowl flaps properly. Maintain sufficient airspeed in climbs. Avoid prolonged ground ops at high power. And 4, constantly monitor your engine instruments, especially CHT and oil temp. If temps climb too high, take corrective action. Immediately reduce power, enrich mixture, increase airspeed, open cowl flaps.
Okay, detonation is bad. What about preignition? Is it the same thing?
Similar results, but different cause. Preignition is when the fuel air mixture ignites before the spark plug is supposed to fire.
Before the spark, what causes that?
Usually it's caused by a hot spot inside the combustion chamber. This could be a glowing carbon deposit, a cracked spark plug insulator, a sharp edge on a valve, or some other piece of overheated material that gets hot enough to ignite the mixture prematurely.
So it starts burning too early in the cycle. What does that do?
Like detonation, it causes a rapid rise in cylinder pressure and temperature at the wrong time, leading to power loss, high operating temperatures, and severe engine damage, often even faster than detonation. It can melt pistons and valves.
Can you tell the difference between detonation and preignition from the cockpit?
It's often very difficult, if not impossible. They frequently occur together. One can even trigger the other. Both result in rough running, power loss, and dangerously high engine temperatures, CHT.
So the prevention strategy is similar.
Yes. The key is to prevent the conditions that lead to either one. Use the right fuel, operate the engine within its temperature, pressure, and RPM limits, maintain proper cooling, and keep the engine well maintained to avoid things like excessive carbon buildup or damaged spark plugs. Proper engine management is the best defense.
Got it. Avoid high temps, use the right fuel, operate smoothly. Now let's end this section on engine tech with something becoming more common, especially in newer or diesel aircraft. FADC, what is that again?
FADC stands for Full Authority Digital Engine Control. It's basically a sophisticated computer system that takes over the management of both the engine and, in many cases, the propeller as well.
Takes over? How so?
It uses multiple sensors to monitor everything: engine speed, cylinder head temps, oil temp and pressure, manifold pressure, ambient conditions, throttle position, etc. The computer then processes all this data and makes real-time adjustments to fuel flow, ignition timing in spark engines, and propeller pitch, if applicable, to achieve optimal performance, efficiency, and safety.
So it's doing the work the pilot used to do with mixture, prop control, carb heat.
Exactly. In a fully FAD-controlled piston engine, especially common with the modern aero diesels, but also appearing on some spark ignition engines, you typically won't find separate mixture controls, prop levers, or carburetor heat controls.
So how do you control the engine?
Often, there's just a single power lever. You move the lever to a detent marked start, idle, cruise power, or max power, and the FAD computer figures out everything else, the right fuel flow, ignition timing, prop pitch, automatically.
Wow, that sounds simple.
It dramatically simplifies engine management for the pilot. No more manually leaning the mixture, no worrying about the MAP RPM dance with constant speed props, no carb ice concerns, as FADs is usually on fuel-injected engines anyway, no manual priming for start. The computer handles it all, constantly optimizing for the selected power setting and current conditions.
What are the benefits besides simplicity?
Usually, better fuel efficiency, and potentially increased power output because the computer can manage things more precisely than a human can. And they typically have built-in redundancy.
Redundancy.
Yes, FATC systems usually have two completely separate but identical digital channels, computer, sensors, wiring. If one channel fails, the other seamlessly takes over, preventing a loss of thrust.
So if a student pilot trains on a FAD-8 aircraft, their engine management workload is significantly reduced.
Massively reduced. It allows you to focus much more on flying the aircraft, navigation, situational awareness, rather than constantly fine-tuning engine controls. It's a glimpse into the future of GA engine management. Outro.
Oh, wow. Okay, that was definitely a deep dive. From the basic dance of the pistons in that reciprocating engine to the almost invisible forces of thrust from a propeller.
And all those critical supporting systems, induction, ignition, cooling, lubrication, fuel control.
It's a lot to absorb, but understanding how it all works together is so empowering for a pilot, right?
Absolutely. We've covered spark ignition, compression ignition, those jet fuel engines, fixed pitch versus constant speed props, how to manage them, the dangers of carb ice, detonation, preignition, even that propeller overspeed scenario.
Knowing these fundamentals really lets you, the student pilot, move beyond just operating the controls to truly understanding what's happening with your aircraft.
That's the goal, being a knowledgeable pilot in command.
So as you continue your training, hitting the books, studying that POH, and getting hands-on in the cockpit, here's something to think about.
Okay.
We spend so much training time focused on the stick and rudder skills, the flying part. But after everything we've discussed today about engine and propeller management, what aspect of that do you think will actually prove most challenging or maybe counterintuitive when you're out there flying in the real world?
That's a good question to ponder. What feels easy now might be different under pressure, or vice versa. Every flight is a chance to connect this theory to practice.
Absolutely. Something to chew on. That's all for this deep dive.
Keep learning, everyone.
Keep flying, stay safe, and stay curious.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.